Thank you for checking out OERB's virtual classroom. I'm Jackie Jackson and I teach Rock and Ratios, OERB's middle level math curriculum. And this video is brought to you by Oklahoma's oil and natural gas industry. Today I want to show you some fun ways to use trigonometric functions to solve real world problems. We're going to use our knowledge of parallel lines and transversals, angles of elevation and depression, and trig functions to help us find distances and heights that would normally be too difficult to find with our normal measuring tools. But first, let's review. Remember that when two parallel lines are cut by a transversal, alternate interior angles are formed. And we know that there are two pairs of those on either side of the transversal. We also know that alternate interior angles are congruent. They're named this because they're on alternating sides of the transversal and on the interior of the parallel lines. We'll be using those today throughout our lesson. Next, we need to review angles of elevation and depression. If you are standing outside and looking straight across to the horizon, you can see your line of sight is labeled. But if you look down toward the turtle, then this has created an angle of depression with your line of sight. Notice the turtle's regular line of sight is parallel to the ground. And then when the turtle looks up toward you, we have an angle of elevation that's created. When the lines of sight are parallel as they are here, those angles are alternate interior angles. And this will take us into our next problem. The last thing we want to review is our basic trigonometric functions. You may have seen the word SOHCAHTOA to help us remember. Each of these are written based on an angle. So the sine of angle A is its opposite side over hypotenuse. The cosine of angle A is the adjacent side over the hypotenuse. And the tangent of angle A is the opposite over the adjacent. So for our first problem, we have a security guard who is working in an observation tower, and he needs to go do a check on one of the tanks in just a little while. He's looking out across in his regular line of sight, which is parallel to the ground. But when he looks down toward the tank, you notice an angle of depression is formed. He wonders how far away it is to the tank when he has to go make his check. Notice that the line of sight and the ground are parallel, and these two angles have been formed that are alternate interior. Using a measuring device like we're going to make later, he determines that this angle of depression is 24 degrees. And since the lines are parallel, the alternate interior angles are also congruent here. So we've got a right triangle that's formed with a 24-degree angle, and then relative to that angle, we notice that the height of the tower is 130 degrees, and we're looking for the distance from the tower to the tank. So we've got to decide which trig ratio would work with this information. So we have got the opposite of the angle, and we're trying to find the adjacent. And so we're going to need to use the tangent ratio. So the tangent of 24 degrees is the opposite, which is 130, over the adjacent, which is x. And solving like we did before, we're going to make this a proportion by putting a tangent of 24 over 1. So we have x times the tangent of 24 equals 130. And to get the x alone, we're going to divide both sides by the tangent of 24. And the tangent of 24 will cancel on the left. So we have x equals 130 divided by the tangent of 24. And if you put this in your calculator with degree mode on, you see that this distance is approximately 292 feet. For this activity, you'll need the following supplies. First, tape. It could be clear tape like this, or masking tape, or even duct tape, whatever you have around the house. Next, you need an index card. If you don't have one of those, you could also use cardboard from something like a cereal box. Next, you need a protractor. Notice this one has 0 at the bottom. It's available for printing below this video if you would like to print it. Otherwise, you could use a regular protractor if you have one at home. You're also going to need a straw and a length of string, probably 10 to 12 inches long. You will need some kind of weight to tie at the end of the string. Paper clips work great. If you don't have any of those handy, maybe a fishing weight or just something small you could tie at the end of the string. And finally, you're going to need a measuring tape. A ruler or a yardstick would also work as well, but I like the measuring tape because it's so flexible. So first you want to measure the length of your foot or your shoe with the measuring tape, and you also need to know your height from your eye down. So I put a piece of tape on the wall at my eye and then use that to measure. To build the hypsometer, you're going to use the end of a paper clip and poke a hole in the paper at the indicated place, push the string through and tape it on the back. Then you're going to put the protractor on an index card to help it be stable and fold the top down so that the 90-degree angle mark is at the edge of the index card. Put the straw on the top and attach with tape, and then tie some paper clips at the end of the string for a weight. We will be measuring the height of this tree, so we need to start by stepping off several paces from the tree. I went 30 paces, turned around and looked through the straw at the top height of the tree. Notice my angle of elevation was 35 degrees. So to solve for the height of the tree, the first thing that I need to do is figure out how far I was standing away from the tree. So as I said, I went 30 steps and the length of my foot was 10.5 inches. So when I multiply those together, I can see that I went 315 inches away from the tree. Next, my height from eye level down was 60 inches. And notice my line of sight to the top of the tree plus my regular line of sight. And when I connect those, it makes a right triangle. So my angle of elevation that we measured with the hypsometer was 35 degrees. And the two sides of my right triangle are 315 inches, as we've determined below, and x, height of the tree, is what we're solving for. So relative to the 35-degree angle, I'm using the opposite side and the adjacent. So that tells me I'm going to need to use the tangent ratio. When you just review, the tangent is opposite over adjacent. So the tangent of 35 degrees is going to equal this opposite side, x, over the adjacent side, 315 inches. Like I did before, I'm going to put this over 1 so I create a proportion so I can cross multiply. This time I have x equals 315 times the tangent of 35. So with my calculator in degree mode, I determine that x is approximately 220.56 inches. Now that's not the whole height of the tree, because remember, we also need to include my height from my eye down, which was an additional 60 inches. So adding that on, we can see that the height of the tree is approximately 280.56 inches. That doesn't really tell us a whole lot because we don't really use values like that in inches. So let's convert it to feet. We know our conversion factor is 1 foot equals 12 inches. So we'll divide by 12. And we can then determine that the height of the tree is 23.38 feet. Now it's your turn. See what objects in your neighborhood you could find the height of. If you do so, take a picture of your project and email it to teachers@oerb.com. And you can also tag us at OERBOK on Instagram or Facebook. You can win a prize.